I came from the Institute of Theoretical Physics, and the results I will present here are the results I obtained during the work of my master thesis under the leadership of Martin Jovka. So, I would talk about the motivation, then I will introduce the Reisner-Nostrum de Sitter metric, horizons in this metric, and the possible degeneracies of the horizons. I will then introduce test particles and analytically solve paths, trajectories of those test particles. Then I will define a continuous coordinate patch over the triple horizon and talk briefly about the collision energy. And in the end, I will visualize all my results on Penrose diagrams. So, motivation. In the 70s, Pirem and Shem were investigating energy extraction and collisions and radiation generated by infalling matter into the Kerr black hole, but they were not concerned with the divergent case. Bañados, Silk, and West discovered their famous effect when the critical particle hits another particle in the proximity of the extreme Kerr horizon, the collision energy can diverge. Zaslavsky generalized these results for a generally rotating black hole and also for the Reisner-Nostrum black hole, extremal Reisner-Nostrum, and then also for the non-extremal. And yesterday we saw the talk from Philip Hayda, who generalized these results for the black holes in magnetized space. So the Reisner-Nostrum de Sitter metric has this form. It's similar to the Schwarzschild metric. The Laps function differs. It's a three-parametric metric with the mass, charge, and cosmological constant. And we can rewrite the Laps function in this form. And if we assume positive cosmological constant, with good agreements with the observations, we can have four real roots of this polynomial. We can get the parameters of the space-time from these roots, although the formulas are really nested. So, as you can see, actually these are real numbers for suitable set of parameters m, q, and lambda. And roots of this Laps function define the killing horizons. For suitable values of lambda, m, and q, we can have up to 3 distinct horizons. This case is called generic black hole. Extreme black hole is when the inner and outer horizon merge into one extreme double horizon. Extreme negative singularity is when the cosmological horizon and the outer horizon merge, and the inner horizon stays distinct. And ultra extreme case where all 3 horizons merge into one ultra extreme, ergo triple horizon. So, test particles in this space-time I describe by the usual equations of motion. Dot denotes the derivative according to proper time or affine parameter. Mu says if the particle is massless or massive. E is the energy, so some constant of motion associated with the time-like killing vector. L is angular momentum, it's conserved in this space-time. And epsilon is the specific charge of the particle. So, it's not easy to solve these equations, but for the photons, for the radial photons, it simplifies the trajectory to this form, and we can do the partial fraction decomposition, and we obtain this integral, and we can solve it by hand. So, the extreme case, we can see that the multiplicity of the horizons manifests here, and in the ultra extreme case, the multiplicity manifests by the third power, and then second and first one. These are just constants, and for the ultra extreme case, we take this one and solve it. And it's actually the Curtis coordinate, known from the Eddington-Finkelstein coordinates. And we define implicitly new coordinates in this manner with some suitable function hx. And if we can see the r minus rt equals tangent x, approximately on the horizon. And this function is defined in this manner, that is 1-to-1 over the horizon or under the horizon separately. So if we do this trick, we can see that the known Finkelstein coordinates are related to the new coordinates, these relations. And if we plot the diagram, the Penrose diagram, we have this kind of thing. So here is the singularity. Here we have the static region. Here is the triple horizon, the x. And here are the spatial infinities. So the shape, the butterfly shape, is caused by this non-trivial function hx. We have to stress that there exists no Kruskal-like coordinates. So this was the only possibility to make an analytic Penrose diagram. So if we want to solve the paths, the trajectories, we have to deal with integrals of this form. So these are well-known integrals. In these tables we can find them, and they have this form. So the n is related to the horizon degeneracy, and yeah, as we see, the -1 corresponds to logarithm, -2 corresponds to 1 over r minus pi, and in the parameter 3 corresponds to the n over r minus pi to the second power. So special particle. We define special particle with a specific charge and this energy. So in this case, the equation of motion simplifies enough, and the polynomial under the square root is just up to the second order. So now we can apply the partial fraction decomposition on this part, and these are the results. So general case, there are ones. In the extreme case, we have 1 for the cosmological horizon, -2 for the double horizon, also the -1 because of the partial fraction decomposition, and -1 for the n. Ultra extreme is 3 to 1. So no big deal there. The critical particles. The critical particles are specific by their specific charge. The RH is value of the horizon, and this is the equation of motion. And we can solve this in the same manner for the extreme black hole case and ultra extreme black hole case, because then we can put this thing in front of the square root, and we have here the polynomial of the second order. So it's nearly the same. The problem occurs for the generic black hole case. This is the equation of motion. It's a nested thing with the polynomial of the fourth grade. And here we decided to make the critical particle for tuned for the inner horizon. So these are the roots of this polynomial. And by the suitable choice of E, we can ensure this sequence of inequalities. So this is negative always also, and we will evolve our particle from R critical through the outer horizon till the inner horizon. The partial fraction decomposition gives us this form with the constants. Nothing tricky there. We can solve this actually, but we have to impose finite integrals. We impose final integration limits, and then this is a well-known integral from the tables, and the solution consists of the incomplete elliptic integral of the third kind and incomplete elliptic integral of the first kind with some constants. This can be true under the outer horizon, and this formula holds up, so above the inner horizon. As we see, here is the divergence. If we substitute the RO for the P, then there is a problem. So this is the solution written. As we see, we have to be careful about the position according to the outer horizon. So in this case, we use the EO or EU. The E3 is a constant. It's a constant and is the price for the finite limits of integration. So once again, this solution can be found in these tables, and the physical meaning of the E3 constant. So these functions diverge on the outer horizon, as we see, and we have to renormalize them and compare the finite parts of them. So if we do not renormalize them and use the wrong value of the constant, the trajectory is not continuous across the horizon. But if we do so, we can make it continuous. It's lengthy, but it's exactly solvable due to some numerical approximation formulas, and can be done. So, the collision of particles. We assume radially moving particles, so these are their 4 velocities with definitions of their parameters. This is well known. The collision energy in the center of mass frame, and these are the well-known formulas. So one of the particles must be critical, because if both are critical, the denominator with the denominator cancels, and there are no unbound collision energies, no infinities. So we actually did the result. We were able to repeat the results for the cosmological horizon, which was done by some Chinese guys. I forgot their name. Sorry for that. And for the double horizon, so we can see for the inner horizon with the new near horizon coordinates, the epsilon goes to 0 on the horizon, and this diverge, this term. So it diverge like a 1 over square root of the epsilon, but only on one side, and namely is the non-static side of the horizon. As Philip said, this kind of motion is, the critical particle cannot approach the single horizon from the static side. The extreme black hole case diverges 1 over epsilon, so it's a stronger divergence, and the new results for the ultra extreme horizon. So, as we see, this term diverges as 1 over square root epsilon to the second power, sorry. And as we see, there's this tricky part, the sign of the epsilon. So under the horizon, in the static region, this would diverge to minus infinity. It's not a good thing, but actually this kind of motion is causally prohibited. Because if we recall the meaning of these functions, x1, x2, it says that the particle moves, so in the static region, this would say that one particle would move to the future and the second to the past in the light cone. So it's not allowed from the causal reasons in the static region. So this, when this function is positive, it's so-called BSW effect, and we can see that this term corresponds to this effect. Okay, so these are the promised Penrose diagrams. So we can see the critical particles, which do cross the outer horizon and do reach inner horizon with the finite value of their proper time. These are the special particles, and they are repulsed by the black hole charge, and they are heading for the other singularity. So this is the extreme black hole case. We have the critical particles. The critical particle is piling up to the horizon, and as we can see here, the crosses denotes the equidistant values of the proper time. It never crossed the horizon, and it reached the horizon with an infinite value of their proper time. On the other hand, the critical particle crosses the horizon, and here has a turning point, so it would continue in this manner and never reach the singularity. And this is the new butterfly-shaped Penrose diagram, and we can see the special particles, 3 of them. They are the only difference is in the time of release, so in the overall constant, and critical particles. So this would be the process, the blue line with the purple line, when the x1, x2 is greater than 0, and therefore it's called the BSW process, and PS process would be this one, when the x1, x2 is less than 0, is negative. So, as you can see, such processes do not occur in this diagram. Okay, so to conclude, as you can see, the special particles are repulsed by the black hole's charge. Only in the general black hole case they can reach the singularity. In other cases they cannot, and they are doomed to go from spatial infinity to the spatial infinity in the globally extended space-times. And we have to be careful about the collisions near the ultra-extreme horizons, since the ultra-extreme horizon separates static and non-static region. And in the non-static region, we can have the PS effect with a stronger divergence, but on the other hand, this effect is prohibited, causally prohibited on the static side. So thank you for your attention.